Hi, hello folks. Welcome to part 6 of these ozone story self-study materials. Today we look at the nucleophilic substitution reaction of haloalkane. So we previously looked at radical substitution to make haloalkanes. So just a reminder of that, you can have something like butane and react it with, say, iodine. And if you expose it to UV light, you will do a substitution. An iodine atom will stick on somewhere and knock off a hydrogen, which goes with the other iodine, and that is radical substitution. If you remember, the point there is alkanes have nothing that actually promotes their reactivity, so it takes something as reactive as a radical to attack them, hence the UV light to turn the I2 into radicals. The story is very different when we have a haloalkane. So if we actually start with our haloalkane, we can add things to it like, let's go water. We would heat under reflux. Remember, you can't abbreviate it like that in an exam. It's just for convenience. And we'll swap the I for an OH, and we'll knock off, where we knock off the I, it picks up the other H from water to make HI. So this is nucleophilic substitution. So why the difference? Let's just, before we go into the mechanism in any depth, let's just look at the reason for it. If we take the haloalkane, in it, there is the carbon where the halogen is attached, is polar. Halogens are more electronegative than carbon, so the bonding electrons will be pulled towards the iodine and away from the carbon, making the iodine delta plus, iodine delta minus, and the carbon delta plus. So what that means is we've now got a carbon with a partial positive charge. And unlike the alkanes then, which don't have any of this, this introduces the opportunity for attack. So this is open to attack by negatively charged species that have a lone pair of electrons. Available. Okay, so let's see how this unfolds with a simple one. No, actually, let's just write the definition of a nucleophile first. So that is, a nucleophile is the thing that can attack in that way. So you've got to be familiar with this word. Earlier in the course, we met electrophile. That was in the reaction with alkenes. See if you can, well, in fact, why not? Just pause, see if you can remember the definition of an electrophile, something that will react with an alkene group. And it's a fairly complicated definition. You should have said a species with a positive charge that can accept a pair of electrons from a region of high electron density, i.e. the alkene group, to form a new covalent bond to it. So that's an electrophile and therefore takes part in electrophilic mechanisms. Nucleophile is kind of the opposite in a way. It's not going to be accepting electrons from the organic molecule with an alkene group that's got lots of electrons. Instead, it's going to be donating electrons to. So the definition here of a nucleophile, again, it's going to be a little bit wordy and a bit technical and something that you need to memorize. This is a species with a negative charge and a lone pair of electrons that it can donate to a positively charged carbon which normally is delta plus, to form a covalent bond to it. Okay, so not exactly short and snappy, but unfortunately that's not just Marcus being wordy. That is the definition, and you need to say it not necessarily exactly word for word, but you do have to have those ingredients, that it's got the negative charge, that it's got a lone pair of electrons, that it uses that lone pair of electrons to form a covalent bond to a positively charged carbon. Okay, if you think about it, you might recognize that in a way that's what's going on in the second step of the electrophilic addition mechanism with alkenes, but that's not something you really need to talk about. Okay, let's look at the mechanism then. So the step-by-step mechanism, you need to know 3 examples of this, the haloalkanes. So example 1, haloalkane plus hydroxide ions. The hydroxide ions, obviously, they don't come in a pot on their own. So e.g., oops, not EQ. E.g. from sodium hydroxide, or could be another hydroxide, potassium hydroxide. Okay, so we'll take a simple haloalkane, and I'll do it full structural just to make it easier to see. So let's have a chloroalkane, and here's our hydroxide ion. So does the hydroxide ion fit the definition of a nucleophile? Species with a negative charge. Hydroxide ions, negative charge, yep, 1 minus. With a lone pair of electrons, does it have a lone pair of electrons? If you do the dot cross diagram, it's got many lone pairs of electrons, so we'll draw in one of them. So always put the partial charge, the ionic charge and the lone pair of electrons on the hydroxide ion. And then what it's going to do is donate that to a positively charged carbon to form a covalent bond to it. So where's our positively charged carbon? Always mark on ionic and partial charges. So whenever you're doing mechanisms, just pause before you start trying to draw curly arrows, mark on charges, whether those are charges on ions or charges on polar bonds. So here we've got the delta plus carbon, delta minus chlorine. Okay, from the definition and from what we've done with mechanisms so far, can you predict? Maybe pause, just have a think logically. What arrows might you have to show the reaction that occurs here? Think about the definition of nucleophile, and just have a play. See if you can come up with something. Start the video again when you're ready. So the definition says the nucleophile has a lone pair of electrons which it can donate to the positively charged carbon. So arrows show electrons going from where they are to where they're going. And so it's going from the lone pair on the hydroxide to the positively charged carbon. And this time we're using a pair of electrons. So don't get mixed up with the radical reaction where we had those half head arrows to show 1 electron moving. Here, a pair of electrons is involved. So we do that. So now that completes the definition. We've got our hydroxide ion with a negative charge and lone pair of electrons, and it's donating the lone pair of electrons to a positively charged carbon to form a new covalent bond to it. Unfortunately, we can't just leave it there because that would be impossible. At that point, the carbon would have 5 bonds. So for this to happen, an existing bond has to break, and if there is a polar bond, it's almost certainly that one that will break because those electrons are already being pulled away from the carbon. So don't break a CH bond typically because there's nothing there sort of encouraging the breaking of the bond. Whereas the polar bond, we've got the electrons being pulled already towards the chlorine. So as that new bond comes in from the hydroxide ion, the chlorine effectively sees its opportunity, grabs the electrons and runs for it. So Marcus's relationship analogies, this is just a classic story of sort of one in, one out. Effectively, the carbon was in a relationship with the chlorine, and then the hydroxide ion came along and substituted. So there's a new relationship between the carbon and the oxygen for the hydroxide ion, and the loss of the relationship between the carbon and the chlorine. Obviously, the chlorine decided to compensate for being so rudely treated by grabbing both electrons from the bond in the process of being chucked off, but we won't necessarily push that analogy any further. I think we're done with that. So what you end up with is a simple swap. We've knocked off the chlorine, we've put on the hydroxide ion, and we have knocked off that Cl. So logically, hopefully logically, where the chlorine has picked up the pair of electrons, only one of those electrons in the bond belonged to the chlorine. The other one came from the carbon. So in gaining an electron that didn't belong to it, that chlorine is now a negative ion. Yeah, okay. Just have a pause and have a look at it. See where the arrows start. See where they go to. And make sure you can see the logic of the story. This is not something that you're supposed to just memorize as a series of random squiggles. So the initiator of this is the hydroxide ion with its lone pair. It donates those two, so an arrow from the lone pair to the positively charged carbon to make a new bond. As a result, the bond between the carbon and the chlorine breaks, with the electrons coming therefore out of that bond. So an arrow starting on the CCl bond, taking those bonding electrons out of the bond to break the bond and going onto the chlorine, which was pulling them towards itself already. Okay, just see if I scroll that off the screen, see if you can repeat that for yourself with just a different one. So maybe try doing it skeletally. So if we had hydroxide ions, well, let's just actually write out the name of the substances. Let's say that we heat bromoethane. No, let's just go a bit more. 2-bromopropane. Under reflux with sodium hydroxide. Draw a mechanism. And I'll encourage you to do this using skeletal formulae, just to have the experience of that. So pause the video, just see if you can recreate that nucleophilic substitution mechanism. Okay, so 2-bromopropane, 3 carbons, bromine on carbon 2. The sodium hydroxide, whenever you have ionic compounds reacting with organic molecules, ignore the metal. The metal is irrelevant. You don't get metal ions. Well, there's a very niche bit of chemistry, organometallic chemistry, but you're not going to meet it anything to do with the A level. So ignore the metal ion. That's just a spectator. Just leave it out completely. You don't get covalent bonds from metal ions to organic molecules particularly. So it's the hydroxide ion. And so we need 2 arrows, one from the lone pair on the oxygen to the carbon where the bromine's attached, and one from the bond onto the bromine. So that's the arrows done with. We'll lose marks if we don't put the partial charges on. So make sure you've got that delta plus carbon and the delta minus bromine. You always put partial charges on in pairs. And then we can head over to the products. And instead of the Br, we'll have OH, and then we'll have Br minus as the co-product. Okay, obviously the sodium ion's in solution, so in reality we would have formed sort of sodium bromide in solution, but we don't need to represent that at all. Right, that was example 1, the reaction with hydroxide ions. I think that's what I called it. Yeah, so let's do the further examples. So example 2. And the next two are just a tiny bit more complicated. This is haloalkanes reacting with ammonia. So I'm going to stick with doing the full structure and a simple haloalkane. So here's our, let's go for fluoromethane this time. And ammonia is NH3. I'll draw that out full structurally as well. And very importantly, we got to think the partial charges here. So we've got the polar CF bond, delta plus carbon, delta minus fluorine. But we also have the polar NH bonds. So the nitrogen is delta minus and all these hydrogens are delta plus. So our ammonia here is going to act as the nucleophile. The definition of a nucleophile with a species with a negative charge, so we got that on the N, and a lone pair of electrons. Haven't got that yet. Does nitrogen have a lone pair of electrons? Think about it. Group 15, 5 electrons in the outer shell, 3 of them taken up in the bonds, single bonds to the hydrogens. So yes, it does have a lone pair of electrons. So in this nucleophilic substitution, always show the attacker with its lone pair of electrons on the negatively charged thing. And then the arrows are going to be the same. So from the lone pair to the positively charged carbon, from the polar carbon halogen bond onto the halogen. And so you might think, well, this, how is this different? Well, there's a little twist here because the thing we're attacking with isn't a negative ion. So we're going to end up with an initially unstable intermediate. We will have attached, let me keep the color scheme. We'll have attached the nitrogen to the carbon with that new bond, but that will still have 3 hydrogens attached. And so that at the moment, the nitrogen has kind of more bonds there than it should have. So this is a little problem. The F is has come off as a negative ion. Hold on a minute, folks. Somebody's knocking on my door. Sorry about that pause. Moment to breathe. Anyway, carrying on. So the key thing to spot here is the charges. Where the nitrogen wasn't an ion as it attacked, and that lone pair which belonged to it went to form a bond to the carbon. Effectively, one of those electrons from that lone pair now belongs to the carbon as its part in that shared pair. It sort of replaces the one that the carbon lost as the CF bond broke. Okay, you might need to listen to this a couple of times to make sense of it. So I'll say it again. The nitrogen had a lone pair of electrons that were its own electrons. It's not a negative ion with an extra electron that it's got from somewhere else, which is why ions are negative. It's just a part of a molecule. Yes, it's got a partial charge on it due to some unequal sharing, but that lone pair of electrons very much are its electrons. So when those pair of electrons go to make a bond to the carbon and become a shared pair, effectively the nitrogen is losing one of its electrons. It sort of keeps hold of one of the electrons in the shared pair as its. The carbon, however, adopts the other one to compensate for the electron that's been stolen from the carbon by the fluorine as that bond broke. So think about the CF bond breaking. The shared pair there, one of them belonged to the fluorine, the other one belonged to the carbon. And so the carbon's losing an electron as the CF bond breaks. So it kind of grabs an electron from that lone pair on the nitrogen. The outcome of that is that the nitrogen will have a positive charge on it. not a delta plus, an actual ionic positive charge because it has lost an electron. Okay, now just note a key, a general principle about mechanisms: charge always balances from left to right. You can't gain charge or lose charge. We're talking ionic charge here, because that would mean making electrons appear or disappear. So if you look over on the left, we've got fluoromethane, that's not an ion, and we've got ammonia, that's not an ion. So we've got no ionic charge on the left. On the right, we've got the fluoride ion with a negative charge. And so somehow we would have magicked a minus a negative charge into being if it was just that. So there has to be a positive charge somewhere to balance that out. So always look at that when you're doing a mechanism step. Look at the ionic charges. If you're somehow magically making them appear or disappear, then you've made a mistake. And you need to look and think, where else is there a charge? So here the positive charge on the nitrogen cancels the negative charge on the fluoride, in terms of charge balancing out, not literally. Okay, so this is unstable. We're not going to end up like this with that positively charged nitrogen. Somehow that's got to become stable. We've got to get rid of that positive charge. That means somehow electrons moving onto the nitrogen. So I don't know if you can just pause and think what might happen to make that stable. See if you can predict something. And the answer is, if you had a go, that one of those NH bonds breaks. And again, there's a sort of a polar thing here. The nitrogen is pulling electrons towards itself already. So it's just going to grab an electron by seizing that lone pair, the bonding pair. I know that's 2 electrons, but one of the electrons in those bonding pairs belongs to the nitrogen anyway. And then it grabs the second electron. So just think logically. If you're thinking, gosh, how on earth do you remember all of this? Try and catch the logic. The nitrogen was unstable because it had a positive ionic charge on it. That means it's got to grab an electron from somewhere. So therefore, an arrow's got to come to it. If it came to it from the CN bond, then we'd have sort of smashed off the thing that had just joined on, which wouldn't really therefore have carried out a reaction. So really the only other source is the NH bonds, and the arrow has got to therefore come from the bond to the nitrogen. So the outcome of that is that we have our N bonded to the carbon there with now only 2 hydrogens. So that's now stable, and we've got an H plus ion as well as the F minus ion. So actually you can take those two and write them together as HF if you want. H plus and F minus is just kind of HF in solution. Okay, so have a look at that. Slightly more complicated story than the hydroxide ions. And as a good way of practicing that, example 3 does something very similar, but with a different substance. So this is a good chance for you to see if you can put this into action. So example 3 is haloalkanes reacting with water. If we take a simple haloalkane again, so let's have fluoromethane, and we've got water. This is going to be nucleophilic substitution. So we must have a nucleophile. Think about the definition of that. And that's going to do an attack that leads to a substitution. And if I tell you that this has a lot of similarity with the ammonia situation, see if you can use that pattern. So just that's the ammonia attacking, doing a substitution, forming an intermediate that then does a little further step to stabilize it. Have a go. Pause the video and start it again when you've had a play to see if you can do the same thing here. Okay, so you should have done a whole bunch of stuff here. You should have marked on the partial charges. So did you remember that? Carbon's delta plus because the fluorine's delta minus, and the oxygen is delta minus because the hydrogens are delta plus. So this is another situation where we don't have an ionic charge on our attacker. It is negative, the oxygen, but not an ionically negative charge. And the oxygen has, well, it has two lone pairs. We only need to draw one. So then you should have drawn an arrow from the lone pair on the oxygen to that carbon. Remember, the arrows must be a bit curly. They don't have to look exactly like mine, but they can't be straight. And then another arrow from the CF bond onto the F. And that will take you to the carbon without the fluorine, now attached to the oxygen, which still has its two hydrogens attached. So we've formed something impossible, sort of unstable. The oxygen does two bonds, not three. The fluorine has been knocked off as a fluoride ion. Doesn't matter which side you draw the charge on. And we have to recognize that just like the N did, the oxygen has sort of lost an electron here, and so it is a positive ion. So again, we've got the thing, there's no ionic charge on the left, and in total, there's no ionic charge on the right. So tick in the box, that balances. We do have an unstable situation though. So just like the ammonia, we have one of these OH bonds breaking with the electrons going on to the oxygen. So it picks up an extra electron there to get rid of that positive charge. And the outcome is then that this is an alcohol, where we had the haloalkane before. So both hydroxide ions and water make alcohols with haloalkanes. Ammonia, and I don't think I wrote this down actually, so let me just add that in. Ammonia forms where you've got a nitrogen attached to a carbon like this. This is known as an amine group. More on those in the second year. Second year, you'll learn to do the systematic naming and more details about amines, but that's all we need to do there for the moment. Okay, one final thing. We've defined nucleophile from the nucleophilic substitution. Substitution itself, substitution, got that right. The definition here is a reaction in which an atom or group of atoms is replaced by a different atom or group of atoms. Okay, that's all for this little chunk. As with all of it, it would be very surprising if you sat there now and thought, yeah, I got that. That's not how learning works typically. So you might well want to skim back through this a few times until it makes sense, and quite possibly make some kind of summary or notes or something like that. So you do what works for you. Don't sit there and go, oh, I just can't learn unless, you know, a teacher does learning to my head. You can, but it might not be as simple as just watching this once through. Okay,